Hey Algebra classes, Mr. Sands here, and I'm going to walk you through the notes that we've taken on 2.2. You've already kind of heard me talk about them, we've gone through them, but I'm just going to make a video, explain them one more time here. So 2.2, chapter 2 is all about linear functions, and 2.2 is specifically about contextualizing linear functions. And we said that contextualizing is a big word that means really to make sense of. To make sense of it either in equation form, in story form, or even in graph form. So again, let's review. What do we know about linear functions? They are going to have straight line graphs, they're going to have a constant rate of change, and they're going to have an equation form of y equals mx plus b. Also, they're pretty much going to look like straight lines here, as we said. So these will be easy things to graph. Really, no parabolas, no curves, nothing like that this chapter. We'll get into that later. Some other key terms that we need to know here. We're going to be dealing with something called the independent variable. We've been referring to it as input, but they are the same thing. So the independent variable is the input. It's what you start with first, or what comes first. Then you're also going to have to figure out the dependent variable. Well, the dependent variable is going to be the output. So if independent variable is input, in, then dependent is going to be out. If you can figure out one, then you can figure out the other. And that's why I have this starred right here. If you can find the input, then the other variable has to be your output. Because we're not going to be dealing with a whole lot of variables here. The m is going to represent our slope or our rate of change, and the b is going to represent our y-intercept, or where this line is crossing the y-axis at. So really we have two variables. We got our x, we got our y. We know that x is going to be our input, we know that y is going to be our output. So anything that's occurring in our x position, that's going to be our independent variable. Anything that's being put in the y position here is going to be our dependent variable. Next slide. So again, we wrote this out because we wanted to talk about how to write things out in shorthand, making sure that we're speaking the same language. So the slope is also known as the rate of change. We can abbreviate that ROC. That's always going to be m. The y-intercept, that's also known as the initial value. We call that the IV. Okay, initial value is IV, and that is usually represented by the small letter b. Now the input is also known as the independent variable, but we're not going to call that IV because that was our initial value, even though this is IV also. So we call our input our independent variable. We can write that in shorthand as just IND. IND for short. Usually that's going to be X, but it could be any other letter. It could be A through Z, really, depending on the equation and depending on the problem. Finally, we've got our output. If our input is our independent variable, our output is our dependent variable. We can write that in shorthand as DEP. That is usually referred to as Y. Sometimes it might be referred to as f of x, or it could be referred to as another variable. So we've been talking about y equals mx plus b. The format is still the same, but the letters may change. So you just got to be aware of that. And we wrote down here, these were some different ways that we can represent a linear function. So we can have a linear function, we can represent it in an equation. That's our math form. That's our y equals mx plus b. We can also represent it in story form, and that would be words. And then finally, we can represent it in graph or picture form. So this was the example we worked through today about the average grade on the Unit 3 test based on number of hours of studying. So we said that looking at this graph here, that this is our independent variable because it's on the x-axis. We labeled that here. So that's our hours of studying. That's why we wrote H for independent variable. We also have our dependent variable, which is always going to be on the y-axis. So again, if we're given a graph, we know that's pretty easy. Also, we know that's got to be the other one. So if this one is H, then this one has to be G. If this one is G, this one has to be H. Whichever one you find out first, the other one has to be the opposite. So don't make things more complicated than they need to be. If we're also given a graph, we can find the initial value fairly easily, because if we're not studying any hours here, they're saying that we would get a grade of 40%. So that's our initial value of 40. Now what does that mean? That means that if you study for 0 hours, we said, you will probably get a grade of 40% or an F. Which is not that great, so that's why we need to study. Now, how much do we need to study? Well, we can actually find an equation to map that. So we had everything, but we just needed to get the rate of change. And so to get the rate of change, we needed to find two different points right here. And I had these, and so this was point 0 and 40, and this was point 2 over and 60. And you notice that a lot of the graphs that we're going to be dealing with within this chapter are going to be fairly easy because they're only going to be dealing with quadrant 1, which is when we have positive numbers on the x-axis and positive numbers on the y-axis. We may or may not be getting into quadrant 4, which may have negative y values. We're probably not going to be getting into quadrants 2 and 3 so much, which is really just 1, mostly 1, maybe a little bit of 4. So that kind of makes it even easier. So we have our 2 points here, 0 and 40, 2, 60. This is our x sub 1 value, this is our second value, or x sub 2. This is our f of x sub 1 value, or our output, this is our second output. So remember, rate of change, abbreviated, rise over run. That's going to be the difference in f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. We know that this number is 60, we put it in there. We know that this number is 40, we put it in there. We know this number is 2, we put it in there. We know this number is 0, we put it in there. 60 minus 40 is easy, that's 20. 2 minus 0 is also easy, that's 2. Now we have 20 divided by 2, that's also pretty easy, that's 10. That's our rock, that's our rate of change, and that's why we wrote it right there. So then after we get 1, 2, 3, 4 things, we know that it's going to follow, turn on the laser, we know that it's going to follow this format of y equals mx plus b. The letters are just different. Our y is our dependent variable. In this case, y is g. Our slope is 10, that's why we wrote 10 in place of m. Excuse me. Our independent variable is not x, it's h in this instance. So that's why we wrote an h for x, and then our initial value was 40. That's why we wrote 40 in place of b. So the equation of this line is g equals 10h plus 40. Problem finished. I told you that I would work through the next one right here in terms of saving up money to get a car. So this is problem 16 from the homework in section 2.2. All of those problems are there. They exist for you guys to just try them out, give yourselves extra effort, extra attempts at working through these problems. If one of them doesn't make sense, that's why I've got the answer key there that you can find on the website. Just Google Mr. Sands Math and you'll get to the website. Remember, if you don't know what the website looks like, it looks like this. And then you can go here for the algebra class. And then you know that Unit 2, linear functions. And we are in 2.2 right here. So you have textbook pages, you have answer keys, and you often will have a video right here. These videos are not made by me, but maybe I will put my video next to this one now that I'm making it for 2.2. Back to the Jamboard. So let's look at this problem. We are not given a graph. Maybe we might want to graph it. Let's see. We'll kind of see what we end up with here. I'm not going to start off with that right away. Let's just read the problem and make sense of it. You started a mowing business so you could buy a 2015 Chevy Camaro when you turned 16. I actually did some research, and this is CarMax. This was the cheapest used 2015 Chevy Camaro. Still not cheap. So start saving your money now if you want to get one of those bad boys. The amount of money, which is going to be represented by M, in your bank account based on the number... Here, that seems to make sense. The amount of money, M, in your bank account based on the number of yards you mow, Y, is modeled by the following function. There we go, I just misspoke. M equals 30Y. So we know M would usually be our slope, but M is not in the position of slope this time. It's actually in the position of our dependent variable. So let's use green this time. So our dependent variable is actually going to be M. So if we figured out one variable, we figured out the other variable. Our independent variable, that's the number of yards that you mow. That's what we can actually change. Okay? If you mow more yards, you're going to make more money. That makes sense. If you mow less yards, you're going to make less money. That also makes sense. We actually don't have an initial value right here because there's no plus or minus anything, so that leads me to believe that our initial value is 0. We must have a goose egg, a big fat nothing in our bank account right now, which is why we need to mow these yards in a hurry if we're going to make enough money to buy this car. Rate of change, well, that's just going to be the number that's in front of the independent variable. So if our independent variable is y, we know our rate of change is 30. So just by reading through that, just by kind of using what we know, and again, I didn't write it down, but you heard me talking about it, always y equals mx plus b. This is going to be our dependent variable. This is going to be our slope or rate of change. This is going to be our independent variable. This is going to be our y-intercept. That's why we filled out everything here. So the contextual description of our initial value. I am actually going to put a text box right here. Might be a little easier for me to type it in this small box. Basically, I already said this. This means that we had no money in our bank account. I guess that's just going to be as big as it is. Okay, contextual description of rate of change. Well, 30 is next to the number of yards, so I'm going to guess that that probably means that for every yard we mow, we make $30. All right, I think that works right there. Now, if we wanted to graph this, actually, let's undo that. We don't need, there's no such thing as a negative number of yards that we're going to mow. We either mow 0 yards or we start mowing yards that have positive integer values, because we're probably also not going to be really mowing half a yard. We're either going to mow a whole yard or not any yard at all. So we're really only going to be dealing with quadrant 1, so I can make a nice big quadrant 1 right here. That's how you can make a graph down and dirty, either on a Jamboard or on paper if you don't have graph paper or a graph already set up for you. Tick marks you can do small one, big one, or 1, 2, 3, 4, make your big ones at 5 and 10 and 15, and that'll usually set you up pretty straight. It worked out here for me even so because I'm using the dotted paper, which helps keep me aligned a little bit better at that. So obviously we're going to have our 0 and our 0 here, and you know what? We can just go ahead and call these as it is. So if we called this 5 and 10 and 15 and 20, what do we need to make our scale at? So if we are mowing 5 yards, well, 5 times 30 is going to be 150. So maybe 10, 20, 30, 40, 50. Well, that would only put us here, so we need a little more room here. So maybe if we called this like 300, 600, 900. Let's or maybe we could do 500. Let's see what does that look like. That would be 1,000, and we would call this. Okay, so this is $500, this is $1,000, this is $1,500. So again, we said that if we mowed 5 yards, 30 times 5 is 150. Let's use different color here. So 150. So this is 100. This is 200. It's going to be about halfway in between, right? So that will be 1 point on our line. If we mowed 10, well. This is basic math right here. 10 times 30, that's going to be 300. So that will be 100, 200, 300. That's a actual nice point right there on the dot. Okay, 15. 30 times 15. 450. So that's 100, 200, 300, 400, 450. And then 20 times 30, that's going to be 2 zeros. 2 times 3 is 6. That's going to be 600. So that's 100, 200, 300, 400, 500, and 600. So you see there's a pretty gradual straight increase there. Can I actually draw this as a straight line? I'm going to try. Concentrate sands. Not too bad, if I do say so myself. And we could even label these if we wanted to be real fancy. So you see that we would have to mow quite a few yards to get to this number. And maybe we're just looking for a down payment. I don't know whether we're looking to buy the whole thing. Maybe you get lucky like I did when I was turning 16 and you buy the car off your cousin for a used car for a much cheaper value. You know, it's good to have friends in low places. But that's how we would solve that problem. They gave us the equation, we figured out the story, and we made a graph here in real time. Pretty cool. And then what I'm asking you guys to do for homework here is make up a function and give it some context. So I am just gonna literally, I think I even had it up here. Oh no, I actually had an idea. I wanted to do steps versus calories. And so I kind of figured this out here. That based on my amounts right here, let's call this 2,200 calories. Okay, so 2,200 calories is what I burn in a regular day if I'm being sedentary. Now, I'm thinking this is going to be our initial value. Okay, because that's really, that's kind of, it's weird. Your body's like a big furnace. It's just consuming energy all the time. So when you sit there and you just think and breathe and your body just does what it does, you still burn calories. That's why if you are eating more than 2,200 calories and you're not really doing anything to burn them off, that's why you start putting on weight, because those are excess calories that turn into extra fat in your body, etc. But that's health class. So if we are burning this many calories without doing anything, that's just a regular day. That's going to be our initial value. Because the problem that I'm interested in is I also figured out that 10,000 steps, that's kind of the magic number of steps people say you should be taking every single day. If you got a tracker on your phone or a fitness watch or something like that, 10,000 steps is the number to shoot for to have an active day where you're getting up and moving around. And what I figured out is that, let's just, for simplicity's sake, let's call that when you take 10,000 steps in a day, you're not being overly, you're not running, you're just kind of walking, you're just getting up and moving around, nothing too vigorous, you're burning 500 calories. So I kind of wanted to make a problem, make a linear function with this. Kind of saying if I burn 2,200 calories in a day, and I burn 500 calories for every 10,000 steps that I take. So maybe we have two variables then. We've got S for steps, and we've got C for calories. Okay, I'm just making this up. Makes sense. S would be steps, C would be calories. So if maybe we had we wrote an equation. Again, I'm just making this up, right? So let's say we have an equation that our total calories burned for the day is equal to the number of steps we take times 500. So 500 calories times the number of steps we take divided by 1,000. So really that should be S divided by 10,000. Because if we take 10,000 steps, that's going to equal 1 right here. So this is my S, right? If I take 10,000 steps, 10,000 divided by 10,000 is going to be 1. 500 times 1 is going to be 1. And then I'm going to add that to my initial value of 2,200. So now I've got an equation that this is, and I could even simplify this if I wanted to, because 500 divided by 10,000, what would that be? Top of my head, 500 divided by 10,000, 0.05. So you could write it that way, but I'm just going to leave it this way because this kind of makes sense with everything that we've stated right here. So usually these don't ask questions. They just say, set this up. So if we wanted to set this up, there we go. There's our quadrant 1 graph that we're looking at. So here's our equation. The total number of calories burned is equal to 500, which is the number of calories you're burning every 10,000 steps you take, multiplied by your independent variable, which is the number of steps that you're taking. So if I take 10,000 steps, that's my goal. I'm going to burn 500 more calories than I am burning already just by doing nothing and sitting on my butt. So let's say we're calling this would probably make sense if we go up by 1,000. So this is going to be calories. This is going to be steps. And we've got our plot of 0 and 0 here. I could do this in Desmos and make it a lot cleaner, but I'm just keeping it all on this page just to kind of make sense of it right here, right now. So we know that if we burn 0, we're not burning 0 calories, we're actually burning 2,200. Let's do red. So there's 2,000. So that would be what? 200, 400, 600, 800, 3,000. So 2,200 would be right here. So this is our initial value. 0 and 2,200. And we know that if we walk 10,000 steps, that's going to be 500 more. So 10,000 is going to be, that's 200, that's 400, that's 500. That's 2,200, 2,400, 2,600, 2,700 would be right there. And then I don't know if we have the next point on this graph. 20,000 would be 1,000 more. So I guess, yeah, it would be pretty close right here. So 3,200. So we have 3 points on this line. Here's how many calories I burn if I take no steps in a day. Here's how many calories I burn if I take 10,000 steps in a day. Here's how many calories I burn if I take 20,000 steps in a day. So my problem could be written out in story format, maybe something like this. So this is really kind of what it would be right here. The problem in word form would say something like the human body burns 2,200 calories in a day, even when you just sit still all day. Also, for every 10,000 steps you take over the course of a day, your body burns an additional 500 calories. Create a linear function to model this. We've done all this. We have our rate of change. We have our independent variable, we have our dependent variable, and we have our y-intercept. So everything is here, and we were able to make up a function on the spot and give it some context. So this is just what I did. Use your imagination, think of something that makes sense to you, and then turn it into a linear function. Make up a story, make sure you have your independent and dependent variable set up straight, and then go ahead and try to graph it. That's going to be, I want you guys to try to do this, at least one good one like this, and you see that I was able to do this in a pretty short amount of time right here with you right now. So I want you guys to make up a function as your homework, and we'll go over them the next time we meet in class. Peace out, guys. See you later.